Let's look at these two functions. Consider the following two functions. F of x equal to x cubed minus 2x, and g of x equal to 4x minus 5. And first of all, let's just refresh our memories as to how evaluating functions work. So I want to find, f of 2. I'm just going to insert 2 for each x. So it's going to be 2 cubed minus 2 times 2, which is going to be 8 minus 4, which is 4. But the important part here is more our ability to insert, not so much our ability to evaluate. In a similar way, we could find g of 1. G of 1 is equal to 4 times 1 minus 5. 4 minus 5 is negative 1. But we could also, put in more complicated things. For example, we could look at, say, f of negative x, which is going to be negative x quantity cubed minus 2 times negative x. When you take a negative thing to an odd power, it stays negative. So that's going to be negative x cubed, and negative 2 times negative x is positive 2x. And in fact, just as an aside here, this is an odd function, right? This is equal to negative f of x, which is negative x cubed minus 2x. Or we could look at g of negative x. G of negative x is 4 times negative x minus 5, which is negative 4x minus 5. Which I will also point out, just because we were talking about last class, this is neither even nor odd. Right? It's not equal to the original. It's also not equal to the negative of the original, which is negative 4x plus 5. Not the same. Neither even nor odd. And we can look at more complicated things, right? I could look at, say, g of x plus 3. Right? I can put in anything I want for x. That's going to be 4 times x plus 3 minus 5, which we could simplify. 4x plus 12 minus 5, which is 4x plus 7. Or we could look at f of, we can even use different letters, right? It doesn't have to be x. I could do f of a minus 2 and plug in that and get a minus 2 cubed minus 2 times a minus 2. And you could multiply it out. I don't really think we need to, but I will. A minus 2 cubed, I'm just going to tell you what it is. It's a cubed. Now that I can I tell you what it is? Yeah. It's a cubed plus 3a squared times negative 2, so minus 6a squared. And then plus 3a times negative 2 squared, so plus 12a minus 8. And then minus 2a plus 4, which we could then simplify further. Not the point. So the point is that if you've got a function, this is just a rule, right? It's saying f of x, you take x and you cube it and then you subtract 2 times it. And that's true for whatever we pick for x, right? F of 2, we cube it and we subtract 2 times it. F of negative x, we cube it and we subtract 2 times it. F of a minus 2, we cube it and we subtract 2 times it, right? Whatever you're putting in for x, you do the rule to it. And for f of x, the rule is x cubed minus 2 times x. For g of x, the rule is 4 times x minus 5. And also true, when we compose, why f of 2? Why not f of 2? I'm just picking things, right? It could have been f of 3 or f of 7, right? We're just kind of trying to show examples where we use any number you want. But right, we could have just as easily said, what about f of, let's not do 7 because 7 is a little big, but what about like f of 5? F of 5 is 5 cubed minus 2 times 5. 5 cubed is 125. 2 times 5 is 10. It's 115. But I didn't pick 2 or 5 for any particular reason. I was just looking for something to plug in. So no particular reason, Fernando, just we needed an example, and that's the number that I decided on, or the notes decided on. But now I want to actually evaluate f composed with g. And I should talk about the language as well here. So if I want to find f of g of 1, this is the way I'm usually going to write it. But some people, some textbooks prefer, and I really don't, prefer to write this as f circle g of 1. These mean the same thing. This way of writing it, I feel like, is much easier to read and say and understand. Here, I think it's not terrible to write this way, but it's better this way. So here this says, I want to know what g of 1 is, and then I'm going to do f of that. Yeah, exactly. So yeah, some people do say fog, F-O-G. It's not an O, it's just a little tiny circle. Right? If you were to look at the typesetting on this in the mathematical textbook, this little circle would definitely look a lot smaller than the letter O. But yeah, fog. So there's actually two ways you can approach this. I'm almost always a work from the inside out kind of person, meaning first, I'm going to find g of 1. Okay, well, g of 1, we actually found already, g of 1 was negative 1. And then I'm going to say, well, then f of g of 1 is f of, well, g of 1 is negative 1. So it's f of negative 1, which is just going to equal, so I forgot what f of x was. F of x was x cubed minus 2x. So it's going to be negative 1 cubed minus 2 times negative 1, which is going to be negative 1 cubed is negative 1, and negative 2 times negative 1 is positive 2. So it's negative 1 plus 2, which is 1. Purely a coincidence that we ended up getting the same number we started with. Yeah. We could also find a different number, right? We could find, say, like, what do I want to do here? Yeah. Let's do, so, yeah, let me point out here. You could also have done this differently if you really wanted. I find it more confusing, but you could have said f of g of 1 is not really, I really think it's, I'm about to write something I think is terrible. It's also right, but you could say, well, f of x, right? You know, the f of x is x cubed minus 2x. So f of g of 1 is g of 1 cubed minus 2 times g of 1. That is also a valid way to approach it, but it just seems gross to me. So I probably wouldn't do it like that, although you certainly could. And then you could plug in g of 1 equal to negative 1. It's the same work, just different work. We could also find something like, I don't know, g of f of 3. I really can't stress enough. When you do this, you have to apply the function that's closer to the number first, meaning it's not g of 3 and then f of that. It's f of 3, whatever that is, and then g of whatever f of 3 is. So off to the side, I'm going to find f of 3. Well, f of x is x cubed minus 2x. So f of 3 is 3 cubed minus 2 times 3, which is 27 minus 6, which is 21. So then g of f of 3 is equal to g of 21. G of x is 4x minus 5. So g of 21 is 4 times 21 minus 5. That's 84 minus 5, which is 79. A very good year. It's year I was born. So yeah, that's how we compose functions when we're trying to compose them with a number, right? So if I want to find anything, in fact, I'm going to give you guys one to try. So why don't you all take...
Can I ask a question real quick?
Oh, yeah, that's why I should turn my volume down. Go ahead, sorry.
Oh, I'm sorry, I didn't mean to scare you. So when we get our 21, do we just plug that right into the g of x?
Correct, right? Because we're trying to find g of f of 3. And we were literally just saying, well, I know what f of 3 is, right? F of 3 is 21. So we say, oh, g of f of 3 is g of 21. And then we just plug that into the g function, which is 4x minus 5, right? So I know it's not written on this side, but g of x is 4x minus 5. So g of 21 is 4 times 21 minus 5.
Gotcha. So then 79 would be our overall answer.
Correct. G of f of 3 is equal to 79.
Awesome. Thank you.
So why don't you guys try this one? Why don't you try, what have I got for you? Sure, that's not too terrible. Why don't you find g of f of 2? I'll give you a minute. Also, I need to, okay, it's been a minute. Before I go here, to answer Fernanda's question, I wouldn't say f of 3 can be any number. It's specifically the number that it is equal to. So for this particular function, f of 3 has to be equal to 21. But I could have picked a different number to plug in, right? I could have picked, right? Here we're doing g of f of 2. Here we did g of f of 3. But we're getting f of 3 specifically by doing the function f with 3 substituted in for x. Let me know if you have further questions about that. For this one specifically, to find g of f of 2, I'm always going to work from the inside out. And that is almost always true when you're working with composition of functions. It's always from the inside out. So I'm going to say, okay, I know that f of 2, I'm just using the function for f. So I'm going to get f of 2 is, we already did f of 2 actually, but I'll do it again. It's 2 cubed minus 2 times 2, which is 8 minus 4, which is 4. And then g of f of 2, well, f of 2 is 4. So that's 4. So I'm really just replacing f of 2 with something it is equal to. And then g of 4, I'm going to use the function. That's going to be 4 times 4 minus 5, which is 16 minus 5, which is 11. So that's all g of f of 2 is. Right. And no, that's all I want to say about it. Yeah. Okay. So, yeah. But then sometimes, well, like when we did f of negative x and g of negative x, sometimes we want to evaluate a function at a place that's not just a number. Right? So we can totally find, g of f of 3 and get 79, or g of f of 2 and get 11. But I also might ask, like, what's g of f of x? Again, remembering that g of x is 4x minus 5, and f of x is x cubed. Was it minus 2x? I think so. Check. Yeah. Okay. So now, again, I'm going to work from the inside out. So g of f of x is g of, well, f of x is x cubed minus 2x. And then g of x is 4x minus 5. Here's what a student showed me they like to do one time. So g of x is 4x minus 5. G of some stuff is 4 times, wherever I have an x, I'm just going to write in parentheses. So g of stuff is 4 times stuff minus 5. And then if it was g of x, right, g of x is 4x minus 5. Now it's g of x cubed minus 2x. It's going to be 4 times x cubed minus 2x minus 5. And then we can simplify this. I'm going to distribute the 4 and get 4x cubed minus 8x minus 5. And that's all the simplifying we can do, right? It doesn't get any simpler. I will also point out, because some people like to see it differently, you could also attack this from the inside out if you really want, from the outside in. So I'm usually working from the inside out, but if you want, you can go from the outside in, meaning you can say that g of f of x, instead of replacing f of x with what it's equal to first, I can think, well, I know that g of x is 4x minus 5. So again, I'm going to say g of parentheses, just like here, g of parentheses is 4 times parentheses minus 5. It's just that here the parentheses is f of x. And then I would replace f of x with what it's equal to, which is 4 times x cubed minus 2x minus 5. It's the same result either way. It just depends on which part you want to deal with first. I'm always like to work from the inside out, but if you want to do this first, say, oh, I know that g of the thing is 4 times the thing minus 5, and then replace f of x with what it's actually equal to. That's also fine. Yeah, what I really want to show you, or what's super important to know, is that g of x and f of g of x are almost never the same. So I want to find f of g of x instead. Again, I'm going to work from the inside out because that's my preferred mode. So g of f of x, f of g of x. Well, I'm going to replace g of x with what it's equal to. That's going to be f of 4x minus 5. And then I know that f of x is x cubed minus 2 times x. So f of a parentheses is parentheses cubed minus 2 times parentheses. And then we would plug in what x was what was in the parentheses, right? Here it's x. Here it's 4x minus 5. I guess I could have. So if we multiply this out, it's not particularly pretty, but I'll just tell you so that you can see that they really are different. 4x minus 5 quantity cubed is going to be 64x cubed. Let's see, plus 16 times 80 minus 240x squared plus 300x minus 125. And then minus 2 times 4x is minus 8x, minus 2 times minus 5 is plus 10. We could simplify that a little bit further. We don't really need to, but I just want to point out clearly this thing here and this thing here are very different. Why is 4x minus 5 cubed? So the reason it's cubed is because the function f of x is equal to x cubed minus 2x. So now I'm doing f of g of x. So it's not just x cubed minus 2x, but it's really g of x cubed minus 2 times g of x. Right? I could write this out a different way, just kind of show the working from the outside in sort of way, instead of the inside out. We could, if we really wanted to, also say that f of g of x, well, again, f of x takes the input, cubes it, and subtracts 2 times it. So f of g of x, we could say, is the input cubed minus 2 times the input. But the input is g of x. And so then replacing g of x with what it's equal to, we get the same thing we got down there. We get 4x minus 5 quantity cubed minus 2 times 4x minus 5. Good. Glad to see that. Sorry, I saw that earlier. I just wanted to keep going so I can clarify it for everybody. So this is kind of the whole idea. When you have two functions composed with each other, then we this is how you do it. That's a good question. Depending on the power, I think a cubic, it is not unreasonable to expect to have you multiply out. Anything higher, I don't think you need to. But yeah, so just to point out how I multiply these out, just so you know, when I'm multiplying out some quantity cubed, I'm using this pattern. I'm using the fact that a plus b cubed is equal to a cubed plus 3a squared b plus 3ab squared plus b cubed. And if it's a minus sign, then every other term switches. So if it's a minus b cubed, then it's a cubed minus 3a squared b plus 3ab squared minus b cubed. But that's not, so I would say, although yes, you should do that if it's a cubic or lower, if you're like multiplying it out, that's not the part you should be worried about, right? Like if you didn't multiply it out, it probably wouldn't be that big a deal. But it's also good to be able to do. I know, it's kind of a mixed message there. If you were running out of time, it is the last thing you should worry about doing. Okay, let's see here. So why are we talking about in composing functions? Well, really because we want to talk about what it means if functions are inverses. Of course I can. And so I want to point out there's not so much an error in the notes as there is a small omission in the notes. So I'm going to share the notes with you just for a second after I write the next thing down. So if I erase it aside, I have. You're welcome. All right, so here's the thing that makes functions inverses. So two functions are said to be inverses, are inverse functions, if f of g of x equals g of f of x. And there's actually one last important part here that isn't in the notes. It has to equal x. I don't think there is any. Oh, I see what you're saying. Yeah, I suppose if I was really simplifying this, Zaina, I would simplify it further as 64x cubed minus 240x squared plus 292x minus 115, right? I would combine those like terms at the very last step. So just to kind of show you guys, if you are looking at the completed notes here, let me share my screen for just a sec. So if you see this here, you can see this says two functions are inverses if f of g of x equals g of f of x, but it's missing the equals x part, and that actually is required because there are functions, not a lot of functions, but there are functions that are not inverses that this first two parts are true. Here's an example. F of x is 3x, g of x is 4x. These functions are not inverses. What an inverse function should do is undo the other function. So let me give you another example, and I'll show you what I mean by this in just a sec. So versus these functions, f of x equal to 3x and g of x equal to 1/3 x. These functions are inverses. I'm going to show it in a second, but I'm just going to tell you, let's look at these. What does this function do? F of x takes x and it multiplies it by 3. So f of x made your quantity 3 times as big. G of x takes x and multiplies it by 1/3. It undoes what f of x did. That is the very definition of being an inverse function. It undoes the thing the other function does. So if you do them both, right, if you multiply by 3 and then you divide by 3, you get back to where you started. Right? If you take x, multiply by 3, and then divide by 3, you're back at x. The same is not true here. If you take x and multiply by 3, and then take the result and multiply it by 4, you're not going to get back to where you started, right? You're going to multiply by 12. But I want to point out what I mean. So here, if I do f of g of x, it's going to equal f of 4x. And then f of x is 3 times x, so f of stuff is 3 times your stuff. And 3 times 4x is 12x. And again, this is kind of a special example, right? There's not a lot of functions where if you compose them in opposite directions, they are equal to each other. But this is an example one that is. G of f of x is g of 3x. And then g of stuff is equal to 4 times stuff. So g of 3x is equal to 4 times 3x, which is also 12x. So here's what I meant. F of g of x and g of f of x are both the same, but they're not equal to x. So they're not inverses. On the other side, over here, f of g of x is equal to f of 1/3 times x. And then f of x is 3 times x. So f of stuff is 3 times your stuff. But 3 times 1/3 times x is just x. And then if we go the other way, g of f of x is equal to g of 3x. But g of stuff equals 1/3 times your stuff. So g of 3x equals 1/3 times 3x, but 1/3 times 3x is equal to x. So these two functions, f and g, are inverses because when you compose them, you end up getting x, right? F of g of x and g of f of x are both equal to each other and equal to x. So they undid each other. F did one thing, multiplied by 3. G undid it, divided by 3, or multiplied by 1/3. I'm really emphasizing this because it's kind of a big deal, and it's very much the very kind of soul of what it means to be an inverse function. An inverse function undoes what the other function does. There's really no better way to say it. I hesitate to use the word cancel each other out because they don't really cancel out. They undo each other. One of them does something, the other one undoes it and gets you back to where you started, which is you always start at x. You start at x, then you do g, then you do f, and if you end back where you started, they're inverses. Okay. Let's look at some more examples. I also point out I don't love the first example that is on the notes, but I'm still going to talk about it because it is moderately important. I don't love the first example because it's kind of a special case. Although it does come up in the notes, I believe. So, yeah. I mean, yeah, it's important because there are functions that we encounter later on that do kind of happen to go with this. So, although we will get very different numbers for f of x and g of x, they'll be inverses, such as the previous example. Well, I mean, yeah. So, like, I mean, for the previous example, right? For this one, you mean, right, Jesus?
No, I was talking about the very first one we did.
No, those were not inverses at all. Like, you mean where f of x was equal to like x cubed minus 2x and g of x was 4 minus or 5 minus 4x or whatever?
Yeah, that one.
Those were not inverses.
Okay.
And the way we know that, so from that previous example, I'll remind you that when we did, let me just suspend. Right, so we had, f of x was x cubed minus 2x. And g of x was 4x minus 5. And when we did f of g of x, or g of f of x, let's do g of f of x, it's a little easier. When we did g of f of x, we got g of x cubed minus 2x, which is g of x is 4x minus 5, so g of stuff is 4 times your stuff minus 5. So I ended up getting 4x cubed minus 8x minus 5. Is that equal to x? No. So since g of f of x is not equal to x, g and f are not inverses of each other. And that's
Okay.
always how we can tell. If you compose g of f of x and you don't get x, not inverses.
Okay. Thank you.
You're welcome. Also, I will point out, right, inverses should undo each other. So I actually will tell you what the inverse of g is. And there's actually a special notation we use. So the inverse notation is this. It is the same function name with a superscript of a -1, kind of like a reciprocal power. So g inverse of x. I want to stress a couple things. Thing one, well, I'll tell you what it's equal to first of all. So here, g inverse of x. So when you have something that's nice and linear, it's really easy to tell what to do to undo it. So g of x takes x, multiplies it by 4, and then subtracts 5. If I want to undo that, I'm going to take x, and I'm going to undo the things in the reverse order. So if I want to undo subtracting by 5, I'm going to add 5. If I want to do undo multiply by 4, I'm going to divide by 4. That's your inverse function. We can check. So here, g of g inverse of x is equal to g of x plus 5 over 4, which is equal to, well, now g of x is 4x minus 5, so g of some stuff is 4 times your stuff minus 5. But the 4's cancel, and then you get x plus 5 minus 5, and the 5's cancel. So you just get x. And then we have to check the other way as well. G inverse of g of x is g inverse of 4x minus 5. And then g inverse of some stuff is your stuff plus 5 over 4. So it's your stuff plus 5 over 4. That's my stuff. -5 plus 5 cancels. So you get 4x over 4. The 4's cancel, you get x. So g of g inverse of x equals x, and g inverse of g of x equals x. That means they're inverse functions because both compositions are equal to each other and equal to x. The other thing I wanted to point out here is that this does not mean reciprocal. G inverse of x does not equal 1 over g of x. Let me just show you, right? 1 over g of x would be 1 over 4x minus 5. That is definitely not the same as that. So you don't just do a reciprocal when you find an inverse. There's a whole process which we're about to talk about. A couple more examples before we talk about the process. I'm going to kind of go a little bit in the opposite order here. So here are a couple examples that you already are kind of aware of, and we definitely talked about their inverse relationship when we talked about them. I'll give you 2 different examples. Here, first of all, we have y equal, not y, I want to use function notation here, sorry. So we could say, sure, f of x equal to 2 to the x, and g of x equal to log base 2 of x. And these are definitely inverse functions. They undo each other. The way we show their inverses. So I'm going to show you something, but I want you to kind of take it with a grain of salt. So what if I looked at, say, g of f of 3? F of 3 is 2 to the 3rd. So that's g of 2 to the 3rd, which is g of 8. But g is log base 2 of whatever. So g of 8 is log base 2 of 8. But log base 2 of 8 is 3. So look, g of f of 3 equals 3. That's great. That helps me affirm, but not actually show that they're inverses, right? This is helping me like, okay, I think they're inverses. I see an example where g of f of 3 is equal to 3, but to actually show that they're inverses, this is not enough. To show that they're inverses, you have to show that both g of f of x, where x can be anything, we're not actually putting in a value for x. You have to show that this is equal to x. And the way we do that, we say, okay, well, that's going to be g of 2 to the x, which is log base 2 of 2 to the x. And at this point, you can either just say it's equal to x, or you could bring down the x in front and say it's x times log base 2 of 2, which is x times 1. But we know that when you take log base 2 of 2 to the thing, you just get the thing, because you're saying 2 to what power equals 2 to the x. In a similar way, f of g of x is equal to f of log base 2 of x, which is equal to 2 to the power of log base 2 of x. And again, this is equal to x because you're saying 2 to what power? Really, so really, this exponent here is the exponent that you raise the base of 2 to get x, right? This is an opponent power, and this power is 2 to that power equals x. But we have 2 to that power, so it equals x. So gf of x equals x, f of g of x equals x, they're inverses. And then another example that's very typical, what's slightly different, is f of x equal to e to the x, and g of x equal to the natural log of x. Those are also inverse functions. They're kind of like some of our most famous inverse function pairs. One more example, but this example is a little bit, there was something I wanted to do here. Let me see if I can. No, you're not my notes. Okay, that's fine. The thing I want to I'll mention, but I won't draw for you, is the inverse functions have this kind of, I'll draw it fine. I can draw things. Let me draw 2 things for you. I want to get one example of me solving for an inverse. So let me graph some things. Yeah, I got enough room here. So on this graph, I'm going to do 2 to the x and log base 2 of x. So I'll do f of x, 2 to the x, g of x, log base 2 of x. So 2 to the x, looks like this. Kind of like that. Doesn't have a vertical asymptote, right? It just gets steeper very fast. And log base 2 of x looks kind of like this. And you can see, hopefully, yeah, sure. So you can see that these inverse functions have symmetry about the line y equals x. And that is something that is always true about inverse functions. The same is true if we were graphing the functions that we just did, where it was g of x equal to, what was the one I had there? G of x equal to 4x minus 5. And its inverse was f of x equal to, let's see, it was x plus 5 divided by 4, or 1/4 x plus 5, if you like. So I'm going to graph these real quick. G of x has a y-intercept of -5. And an x-intercept, if I set this equal to 0, I'm going to get positive 5/4, which is not very big. So I'm just draw it like that. So that's 0, -5, and that's 5/4 comma 0. And notably, the inverse function line has the opposite, or the inverse, I should really say, intercepts. Instead of having 0, -5, it has -5, 0, right? If you plug in -5 for x, you get 0 for y. So right, we get -5, 0. And the y-intercept, if you plug in 0 for x, you get 1/4 times 5, which is 5/4. So we get 0, 5/4 instead of 5/4, 0. So this one looks kind of like that. And they're exactly, again, symmetric about the line y equals x. And they would intersect each other on the line y equals x. It's kind of cool if they intersect. There's this reflection term. Okay, the reason I bring this up is because the next example is a little bit more problematic. So the next example of inverse functions are y equal to x squared, or f of x equal to x squared. I'm sorry, I'm just trying to look at something here just to make sure. Yeah, so, oh, sorry, I've got f of x equal to the square root of x, and g of x equal to x squared. And the problem with this is, well, let me show you. If we graph these, square root of x is perfectly fine. Square root of x is the usual shape, right? 1, 1. There's your g of x. Now the problem is x squared, well, x squared does this to the right. Right? So they definitely look like they have that symmetry, but the problem is x squared also has this left side. And graphically, inverses really should reflect each other across the line y equals x. But the problem is we don't have the reflection of this down here. And the reason we don't is because if we had this piece, this g of x wouldn't be a function because it would fail the vertical line test. So here's the deal. For functions to be invertible, they have to be one-to-one, meaning they have to pass what's called the horizontal line test. This green function, if you have all of it, is not one-to-one. There are different x values that give you the same y value, right? X could be -3 or +3, and either one of those squared is going to be +9. So the way we fix this is we say, well, I'm going to restrict the domain of this function so I don't have that. So we restrict the domain of g of x equal to x squared to be where x is greater than or equal to 0. The remaining piece doesn't have a problem, right? It doesn't fail the horizontal line test, and it does have an inverse. So these two functions are inverses. Let's check. G of f of x is g of the square root of x, which is the square root of x quantity squared. If you take x, it already has to be positive. Take its square root, you get some number, and then if you square it, you get back the same number you started with. On the other hand, f of g of x is slightly more complicated. That's f of x squared, which is the square root of x squared. Now here's the thing. The square root of x squared is actually not just x. It's the absolute value of x. If x is positive, great. Right? Like if x is 5. 5 squared is 25, square root of 25 is 5. If x is -5, -5 squared is 25, and the square root of 25 is 5. That's why it's the absolute value. But since we said x had to be non-negative, that means this is equal to x because x is greater than or equal to 0. So it works. G of f of x equals x, and f of g of x equals x, if we get to assume that x is already non-negative, which we did. So these are inverses. I would say don't worry too much about that part of it. It's just something that has to be addressed. And it does come up later when you take Calc 1. All right, we got time for one example. We'll definitely continue. So tomorrow we'll continue talking about inverses and how to find them. And then we will also talk about the difference quotient. So let me give you one example of how to find an inverse. Yeah, sure. So let me give you maybe. So let's say we had f of x equal to 4x cubed plus 1. And I want to find the inverse function. There's a process, it's a 4-step process, and only really one of the steps is actually where you have to do any work. So the first step is dumb, write it as y equal to 4x cubed plus 1. The second step is also dumb but necessary. You want to interchange x and y. So every y becomes an x, every x becomes a y. By the way, interchanging x and y is kind of the important part, right? You're interchanging the x and y coordinates. Instead of getting the point 4, 2, we're going to be getting the point 2, 4 if those were our functions. So when you interchange x and y, that's when you actually get the inverse relationship. And then the rest is just solving for y, which is the part where we actually have to do some work. So solve for y. So subtract 1. Divide by 4. Take the cube root of both sides. So you end up getting y equal to the cube root of x minus 1 over 4. And then finally, the last step, which is also kind of a nothing step, is instead of writing y, we're going to write not f of x, but f inverse of x. And that's the process for finding an inverse function. Let me give you one more, because I have another minute. I can do a fast one. Sure. Another pretty not terrible one. So if my function was, I don't know, let's make something up like 7x plus 9. To find the inverse, I'm going to write y equals 7x plus 9. I'm going to rewrite it, interchanging x and y. All y's become x's. There should only be one y becoming one x. All x's, which there can be more than one x, should become y. Solve for y. So subtract 9, x minus 9 equals 7y. Divide by 7, or multiply by 1/7. 1/7 times x minus 9 equals y. And then finally, write it as the inverse. So the inverse is going to be f inverse of x equals 1/7 times x minus 9. Or you can even multiply it out. You don't need to, but if you wanted to, you could write it as 1/7 x minus 9/7. That's your inverse function. And importantly, they undo each other. F of x takes your input, multiplies it by 7, and then adds 9. The inverse undoes that by first taking your input and subtracting the 9 that you added, and then after that, dividing by the 7 you multiplied by. Totally undoes what we did. Same deal here. This function takes your input x, first it cubes it, then it multiplies by 4, then it adds 1. The inverse is going to undo all those things in the opposite order. So first it's going to undo the one you added by subtracting 1. Then it's going to undo the 4 we multiplied by dividing by 4. And then lastly, it's going to undo the third power by cube rooting it. So some functions, not all functions, but some functions like this where you can kind of see what you did in what order, it's really kind of easy to also see what you undo, how to undo it in the opposite order, doing the reverse operation. But yeah, we'll definitely talk more about this tomorrow. So I should stop talking because it's 11:51. And yeah, I will. Is that a y? Probably. Well, let's see. Here, that's a 4. Sorry, that's an x minus. That's the cube root of x minus 1 divided by 4. I know it might look like a y because sometimes their writing is terrible. Cool. All right, that's all I got. I'll see you guys.